Hello and welcome back to another lecture. In this lecture we're going to talk about designing a bearing wall. Here's the problem on a board. It says design a concrete bearing wall using ACI. We're going to use the imperial method, and the bearing width of each the wall is supporting a bunch of beam at 7 feet on center. I will show you in a figure in a minute. And the wall is considered to be laterally restricted at the top and bottom. So our K is equal 0.8, and to be restrained against the rotation, neglect the wall weight, and F prime C is equal to 3000 psi, and steel is 60,000 psi, and a beam reaction share are dead load 30 and life load 30. Life load is 8 kips. So let's shut this off and. So if you take a look at the sketch right here, we have the beam, which is 7 feet on center, and the wall is about 16 feet tall. It's connected to the footing. We want to find out what is the design this wall. And if we look at the plan view right here, the beams are basically supported by the wall every 7 feet. And so let's get to work. Okay, the first thing we're going to do, we're going to go to ACI 11.3.1.1. Let me bring that up. So here's the 11.31 for ACI, minimum wall thickness. So minimum wall thickness shall be either A or B. Either this one, 4 inch, or 1 over 25. So let's go ahead and work on this wall thickness. I hope you like, I think I like, I go for cheesecake today. Although I like carrot cake today. Today's cheesecake sounds good. And always, and if you're watching this video, remember, you awesome. Don't let anybody tell you different. You are great. Do not sell yourself short, for you are priceless. There's a reason. All right, let's get back to work. So that ACI tell us, okay, we have two. One was H is equal 4 inch. It was A, and B, it said has to be 1 over 25 time the height of the wall, which was 16 feet, time make it a inch, 12 inch. That's per foot. And that comes out to be 768. So the bigger number control, this controls, and we're going to say, okay, use 8-inch wall. That's what we're going to use for the thickness of the wall. So that's our H. Then we're going to go to ASCE 722. We're going to calculate the load. Our PU is equal, which is the reaction that's been given to us, for 1.2 times dead load plus 1.6 times life load, which was 18, and our total load going to come out to be 64.8 kip. And this is basically our Vmax, or reaction, beam reaction. If we come back up here, that's a reaction of beam right here. That's what we found right there. And that's a 64.8. That's from the beam itself. All right, so the next thing we're going to calculate is the ACI 14.5.61. Check the wall nominal bearing strength. What this means, it's the load on top of the wall. It's the concentrated load, which is the beam bearing on top of the wall. Is the wall's bearing pressure strong enough to take that load from the beam? That's what we're trying to do. And we use this a lot in timber because timber is kind of soft, and we'll always check the bearing pressure. So we're doing the same thing here with the concrete. And let's go to ACI 14.561. Actually, I got it open right here. We make it bigger so we both can see it. And right here, what is applied for is other. It's a 0.85 F prime C time A1. This is what we're going to use. Okay. So we're gonna put a phi factor to it. Phi time 0.85 f prime c time area a1. So that's a 0.65 time 0.85 time that's a 3,000 pound concrete, and the area we're gonna use is a 8-inch by 10-inch, because we said the width gonna be 8-inch. So when the beam itself is about 10-inch wide and the wall is about 10-inch wide, so that's what the area comes out to be right here, area, and that's gonna come out to be 132.6 kip, which is bigger than our load on top of it, and we are okay. So this is the capacity. This is a bearing capacity, which is bigger than a load, and that's what we like. So next we're going to go ahead and calculate the load distribution per ACI 11.2.3. So the load distribution, sometimes we used to use a tributary area beam spacing, could be from beam to beam, which we did tributary with, or the ACI has a different, which I like it, they came up with a different formula. Let's take a look at the ACI 11.23. Let me bring that up. I got them in a PowerPoint right here. Hold on. There we go. So right here it says, unless otherwise demonstrated by the analysis, the horizontal length of the wall considered as effective for resisting each concentrated load shall not exceed the lesser of the two, which one is a center to center, which is basically a tributary area, distance between the load, tributary width, and the bearing width plus 4 times of the wall thickness. So either this one or that one. All right, this looks good, huh? I want to have some spaghetti meatball. All right, let's go back to work. So A, we're going to have was a center to center. Center to center. That was a spacing, which was 7 feet 0 inches. And that one comes out times 12, become 84 inch. B was a set bearing width, which was 10 plus 4 times h, which is 4 times 8. And that one comes out to 42 inch. And I said the lesser two I'm going to control, so this one is going to control. Okay, we're going to go with that one. Okay, so next we're going to go ahead and do the design strength of the wall per ACI 11.5.3.1, which is, I wrote the equation down, but let's go to the ACI itself, look at it. And there we are. It's right here, this 11.5.31, and there's the equation. If the resistance of the factor load is located within the middle third of the thickness of the solid wall, then our PN can be calculated like this. Of course, we just put a phi factor to it. Let's look at this, what KL, where we get that number 0.8. I have in the PowerPoint. There we go, right here. Oh yeah, that looks good. So if you look at the table 11.5.3.2, it says the boundary condition for K. This is like for buckling we did with steel design with timber. And if A, restrained against rotation at one end or both end, basically fix that bottom, fix the top, it's going to be 0.8. And if it's going to be pin, it's going to be 1. But anyway, so let's go back to the writing. And we're going to plug in all the number here. That will become equal 0.65 times 0.55. F prime C was 3. And our area, you got to be careful for the area. The area is going to be 8 inch. This is the wall thickness multiplied by the other length is right this number that controls that 42 inch. So time 42. And then we're going to time 1 minus KL was 0.8 and length is 16 feet, so it would be 16 times 12 meter per inch, and divided by 32H, and then square the whole thing. And that comes out to be feet times PN equal 230.6 kip, and that's bigger than our load, which was 64.8 kip. So we okay right here. It's bigger than applied load. Okay, finally we're going to go ahead and select the reinforcements. They're really good reading at 11.7.2 and 11.61. Let's go take a look at the one of them, and then we'll go take a look at the other one. Look at the 11.62, and they give us for the maximum spacing, calculating the area of the vertical and horizontal bar. But for the spacing, if we're gonna see the we're gonna see right here, it says spacing S longitudinal bar in a cast in place. Ours is going to be cast in place. It's not going to be precast. It's going to be not exceed the lesser of 3H or 18 inch. So we're going to take a look at this and then see what we're going to come up with. Let's go back to writing so we figure these out. Okay, so max spacing it's a 3 times H, which is 3 times H, which is equal 3 times 8, that's 24 inches, or 18 inches. So we're going to select the 18, which is lesser of the two. And then the other one said the vertical steel area of the steel, and that's 0.0012 times the area, which was 12 times 8, and that's going to be 0.115 inch square per 1 foot section. And if we put that in, we're going to say, okay, use number 4 bar at, we said 18 inch on center, and number 4 bar, the area, let's take a look at that, see what number 4 bar has for the area. So number 4 is 0.2. 0.2, the area is equal 0.2 inch square. However, we're going to do it at 18 inch on center. Make sure we're not going to be less than that number. So we're going to say, okay, 0.2 times 12 divided by 18 inch spacing, and that gives me 0.133, which is bigger than 0.115. We okay. So we're going to use that. And then the next thing we're going to do is go to horizontal bar, and AS is equal 0.002, and that's per the spec up there, times 12 times 8, that's equal 0.192 inch square per foot. So now the same way, if we use number 4 at 12 inch on center, we'd be good. So our wall is going to have rebar like this, and then we're going to have also this way. So if I look at the whole plan view of the wall, looking at the side view of the wall, and the rebar is going to be going this way, one of the mat anyway, and it's going to come this way. This is the vertical one. One of them is on an 18 inch, the other one is a 12 inch on center. So when I used to do work at I wasn't on a job, I used to make them like either 12 by 12 or, and they're going 12 by 18, but they're not, back then it's not that, you know, it's not going to kill anything. And another thing it doesn't show in here, you really, one of these vertical bars that are coming down, you should bring them down and make a dowel bar out of them coming down like this. Let me change the color so you see. It should really come down like this and make it kind of like that, then tie into the footing. It shouldn't be just like that. Okay, so this is it, and hope you like this, and give it a thumbs up. Thank you. Have a good day.